Today's topic of discussion is solenoid. Now, when a coil of wire, usually in a cylindrical form, when carrying electric current, it will behave as a magnet. So, this is the coil of wire you can see, and the current is passing through this coil. It is seen from this. Okay, so it is a helical coil. Say current enters like this and then it goes in this direction. Okay, it goes like this. So current flows in this direction. Or if I choose another color, then this current can be shown. Say this is the direction of current. This way it goes. This way. Okay. So this is the direction of electric current. If you see from this end, if you see from this particular end, okay, from this end if you see, then the current is flowing in this direction, that is in the anti-clockwise direction. So if you are looking at the coil from one side and if you find that the current is in anti-clockwise direction, then this side of the coil will behave as north pole, and if you look from this side, then the anti-clockwise current which can be visible from this particular end will be appearing to you in clockwise direction. Try to understand. If you see from this side, then it appears to be moving in anti-clockwise direction. If you look from this end, right hand side, then that will appear in a clockwise direction. And if the current is found to be in clockwise direction from the side from where you are looking the coil, then that end will behave as a south pole. So when current is passed through this kind of coil, then it will behave as a magnet. It will behave as a magnet. Okay. So meaning of this solenoid. Okay, so solenoid you understood, a coil of wire in a cylindrical form, that when carrying a current it will behave as a magnet. Now what is the meaning of very long solenoid? When length of the solenoid is very large in comparison to the radius of the solenoid, then it is said to be an infinitely long solenoid or very long solenoid. You can see here this is the length of the solenoid. If this length is large in comparison to the radius, this is the radius, okay, then this is said to be a very long solenoid, or it can be considered to be a infinitely long solenoid. Okay, so this is the condition for infinitely long solenoid, that the length must be very large in comparison to the radius. Length must be large in comparison to the radius of the solenoid. Okay. Now the solenoid consists of long wire wound in the form of helix, where the neighboring turns are closely spaced. That you can see from this figure, that it is, or a very long wire is taken and this wire is wound in the form of helix like this, and the turns are kept very close to each other. They are very close to each other. Okay, and this is called the solenoid, we can say. Okay, so the solenoid consists of a very long wire which is wound in the form of helix. Okay, so very long wire is taken and it is wound in the form of helix. Okay, and neighboring turns are very close to each other. So each and every turn will be behaving as a circular loop. Okay, and the circular loop will produce magnetic field, or we can say each and every turn of the helix is going to produce the magnetic field. Okay, and then you have to take the vector sum. The net magnetic field is the vector sum of the fields which are produced by each and every turn. Here the wire which is used is an enameled wire. Okay, it has an insulation on it, okay, which is used for winding so that turns are insulated from each other. Okay, so this is the construction of solenoid. Now we want to find out the equation of magnetic field of a solenoid. Okay, this is the solenoid. A cross section of the solenoid is taken. Okay, the whole structure which I have shown you, okay, earlier here, that is cut from this. Okay, here the cut is taken, this part is opened up. Then what will happen? The current which is flowing, okay, if it is flowing from inside, okay, then from this point that current will be going inside, and from this it will be appearing to you coming out. Say for example you have a circular ring like this in a 3D shape. Then if the current is in anti-clockwise direction, then from the upper part the current appears to be going inside, and from the downward part it appears to be coming out. So you are cutting it from here as such. So you can see that the current is going inside from the top and coming out from the bottom. Okay, now that part is shown here, okay, in this figure. This is a cross section, or rather we have taken a cut, okay, and it is taken here that the current is coming out from the upper part. Okay, current is coming out from the upper part. Dot shows that current is coming out, and the cross here shows that current is going inside. So current is coming out from this and current is going inside from the lower part. Okay, so this is the cross section, rather we cannot say cross section, but a vertical cut is taken, that of the solenoid. Okay, now we consider a rectangular Amperian loop ABCD. Here rectangular loop is taken. We will find out the magnetic field of solenoid by considering the Ampere circuital law. Okay, we are taking an Amperian loop ABCD. Okay, so here the loop is taken, that is ABCD. This is the rectangular loop. Okay, along CD you can see CD part. Okay, the field is 0 as CD section is out of the solenoid. Now for the solenoid, try to understand the magnetic field is within the solenoid. Outside the solenoid the magnetic field is almost 0. So this CD section is outside the solenoid, so the magnetic field here is 0 where CD is lying. Okay, so here magnetic field is 0 at CD. Okay, at CD the magnetic field is 0. Along the transverse section BC, now you see this section, this is BC section and the other section is AD. So these two sections you can see that magnetic field is along the axis of the solenoid. This is the direction of magnetic field. Now try to understand. The magnetic field is in this direction, and the part, this part, okay, this part, that is AD. Okay, this part is AD and the other part is BC. Both are perpendicular. You can see this part is perpendicular to magnetic field. This is also perpendicular to the magnetic field. Thus these two sections make no contribution. Now see, we are right now considering the Ampere circuital law, and in context of the Ampere circuital law we are thinking about all these things. See, Ampere circuital law is B dot dl is equal to mu 0 I. Now you try to understand this part. This is outside the magnetic fields, or we can say here magnetic field is 0. So this is not going to contribute in this B dot dl. So this part has no contribution, or this is making the integration to be equal to 0. Here this part is perpendicular to magnetic field. Now B dot dl, so B dl cos 90. So cos 90 is 0, so this part is having no contribution. Similarly, this part you try to understand, that is also perpendicular to magnetic field. So again this BDL, as rather B dot dl for this section will become 0. We have to take the integration over closed loop. Line integration of magnetic field we are taking. So part by part, this part is outside magnetic field, so B is 0, so this is not contributing. Here this is perpendicular, that is B and DL are perpendicular to these two things, so it is also not contributing. Now one part is only remaining, that is AB part, okay, which is found to be within the magnetic field, and it is in the direction of magnetic field. So B dot dl if you take, then theta between this and the magnetic field B is 0. Angle between this AB part and the magnetic field vector B is 0. So now let the field along AB, this part which is to be considered now, okay, AB part, field along this AB is capital B. Thus the relevant length of Amperian loop is now L is equal to H. Now Ampere circuitry law you must remember, it is BL is equal to mu 0 IE. L is the length of loop. So length of loop is H. Say this much is H. AB is equal to H. Then length of the loop is H. Length of the loop is H. Okay. So let us consider that small n is the number of turns per unit length. That is how many turns are there in 1 centimeter. If you consider the length of the loop, which is effective length is H, okay, that is equal to AB. You can see how much loop is now enclosed. This much loop is only effective. So the length of this part, if you consider H, the number of turns per unit length is N, then total number of turns which are there within this particular region, that of length H, will be equal to N into H. Okay, and that is shown here, that N is the number of turns per unit length, therefore NH is the turns which are enclosed by the Amperian loop. Okay, therefore the current which is enclosed is number of turns multiplied by the current which is flowing through the solenoid. Let I is the current through the solenoid. So current enclosed by this will be NH into the current which is flowing through it. So this will be the effective current. Okay, where I is the electric current which is flowing through the solenoid. So if you now use the Ampere circuitry law, BL is equal to mu 0 I, here L is equal to what? It is H. Okay, L is equal to, we have H. Okay, B we want to find mu 0. Okay, IE is nothing but NHI. So here H will be cancelled out. So you will have B is equal to mu 0 Ni. Okay, B is equal to mu 0 Ni. So this is the magnetic field which is produced inside the solenoid. The direction of the field is given by the right hand rule. Okay, the solenoid is commonly used to obtain a uniform magnetic field. How the right hand rule is used? You have to curl the fingers in the direction of the current flowing through the turn. Say for example, if the current flowing through the turn is in this direction, then you curl your finger in this direction. Your fingers are curled in this direction, then the thumb will remain in this direction, and that will give you the direction of magnetic field. Okay.